So here's a long list of different regularization methods. We can limit the size of the network. This is a little bit about, against our philosophy of having very flexible models, but we have seen that it's in, for example, image recognition, that it's a very successful strategy with convolutional neural networks where we have a lot of weight sharing. We can perform what is called early stopping, also very nice technique in the way that we also there save computation time, because we don't want to run for 1000 iterations. We can stop sometime before when we don't see any more improvement on the validation performance. Then we have weight decay, which is also corresponding to having a prior on the parameters, and then we are doing a maximum a posteriori estimation. We can have what's called data augmentation, where we exploit the symmetries we know are in the data. So for example, with MNIST again, we can make distorted version of the digits. We know this will still look like the original digits, or should be classified as the original digits, but they are different. In that way, we explore the manifold of digits more, and therefore also achieve higher generalization performance. Then we can add noise, as we saw in the previous example, and we can have parameter sharing, as I said. We can also have sparse representation. I will not talk so much about that. Ensemble methods is another way to do this Bayesian approach. It's kind of a poor man's Bayesian approach, and we'll see dropout as an example of that. And then we can also have what is called adversarial training. So that means that we exploit that there are some directions in the input space where the model is easily confused, and then we produce new examples in those directions in order to make the model more robust to these kind of adversarial examples. Yes, so let's go through some of these methods. So first of all, limiting the size of the network. So this can be done in different ways. We could, for example, reduce the input dimensionality. This is very classical, for example, with principal component analysis. So we look only at those directions, input space that have the highest variance, and we give that data projected on those directions as input to the network. This goes a little bit against our end-to-end philosophy, so maybe we should look for something else. Early stopping can be understood a little bit from this posterior approach, and is illustrated in this learning curve, where you can see that the training error goes down and down and down over time. So that's on the x-axis, but the validation error has its minimum around, let's say, 25-30 iterations, and we can stop there, and then we can hope that our test error will also be lowest at this point. So this is something we use all the time as a reasonable heuristic. I would actually prefer to have methods where we have set up the model such that we can run it to the end and then get the best solution. But this is a good pragmatic heuristic. Weight decay is the idea there is that we have first our training cost, so our minus our log likelihood, and then we add another cost that penalizes the complexity of the model. So if you think about a tangent hyperbolic network with hidden units, tangent hyperbolic networks, then we know that the larger the weights are, then the more the more non-linear the decision surface will be. So there it makes sense to penalize the size of the weights. We can do that by either L2, so we penalize the squared length of the weights. So this two pipes around here means the length of the weight vector, and it's squared there, and that's L2. So we add lambda half times the length of the weights in L2 regularization. L1 we add lambda half the one norm of the weight vector, and that when we minimize the cost with that penalty at L1, then it's easy to show that this will give weights that will become 0. So it will give a sparse solution if lambda is large enough. So this is illustrated here. So you can see we have our maximum likelihood solution indicated in this kind of two-dimensional example indicated by these contour lines and this W star. Then if we add regularization on the left, we have L2 regularization, on the right we have L1. Then you can see that L2 will move our solution towards this W tilde point, whereas we get a different W tilde point for L1, where you can see that we actually move more towards one of the axes. So in this example, we almost have wiped out the first weight. Yes, here's a little bit of discussion about the connection between Bayesian inference and these regularization methods. This is a little bit a vague connection, because in Bayesian would, as I said earlier, integrate over the parameter space when we make predictions and not look for a single point. But the connection is that you can look at the penalty with regularization as kind of minus the log posterior distribution. So or proportional to that, or up to a constant factor equal to that. So we actually now, with regularization, we are maximizing finding the maximum point of the posterior distribution. Yes. So of course a very important question every time we introduce a new parameter is, how do we actually set this? And this lambda parameter is a so-called hyperparameter. We have many other hyperparameters, and we have the question always how to set the number of hidden units and so on. So if we have only a few of these hyperparameters, then we can use the validation error and a grid search or something like that to find the parameter. If you're Bayesian, then you would make a so-called hierarchical model and put also a prior distribution on this parameter, and then infer that together with the normal parameters. So this was a little bit about the classical way to do regularization. Next, I'll talk about other methods.